just landing back to the lunar South Pole with another commercial company.
And Leah and I are at Intuitive Machines' facility here in Houston, down the street from NASA's Johnson Space Center. About 6 hours ago, our lander named Athena completed her descent orbit insertion, or DOI, burn. That main engine firing started lowering Athena's altitude towards the lunar surface in preparation for landing. Their entire team, their families, friends, and stakeholders are all watching about 10 minutes down the road from Mission Control at the Lone Star Flight Museum, waiting for Athena's final engine burn to the surface.
Now that DOI, or descent orbit insertion, is complete, Athena is operating autonomously, but flight controllers still have the option to make some adjustments. The lander is expected to coast from 100 kilometers above the surface down to about 10 kilometers, and then she's expected to fire her main engine for powered descent. That's one final engine burn all the way through to touchdown.
And Leah, we have made some late changes to PDI's profile to accommodate for some uncertain variability with recent landing measurements. We now expect PDI pitchover to happen about 450 meters above the lunar surface versus the originally planned 400 meters. We're doing this to allow a little extra time for flight controllers to confirm and manually screen altitude measurements before ingesting those measurements into the navigation filter. We do have additional navigation aids on this flight that were not available to us back in our first mission for IM-1. Now let's take another look back inside of Nova Control. Our mission and activity directors are sitting at the top left of your screen, and they're supported by about a dozen additional flight controllers surrounding them in this circular Mission Control Operations Center. It will take the entire team, including a dozen backroom support staff, to land Athena today, Leah.
If we receive confirmation that Athena has touched down, the lander will go through several measures to make sure its liquid methane and liquid oxygen engine is safe. And then flight controllers will prioritize vehicle health data before sending images, approximately 2 hours after landing.
And right now, flight controllers are monitoring Athena's health and trajectory ahead of her autonomous landing sequence. That begins with powered descent initiation at approximately 11:16 a.m. Central Time for a landing at approximately 11:30 a.m. Central. From this angle, you can see a large monitor on the wall inside of Mission Control. What they're looking at is up on your screen right now. It's the room's situational awareness tool called the Viz, directly in front of the mission and activity directors.
The Viz is an animation representing real-time telemetry data feeding into Nova Control. Nova Control receives the data and runs it through a video game software, then generates a visualization of that data. It's a useful tool for keeping track of what Athena is doing in space. The white line you see right now is pointing to the moon. There are also some other color lines you might see pop up, like a blue line, that's the past and intended trajectory. The yellow and the green lines are pointing toward the sun and the earth, respectively. And at different points during landing, you might see some different color cones appear. Those are antenna arrays used for line of sight communication back to Earth. We're going to show the Viz periodically throughout this show to check in on Athena, and we intend to leave the Viz up during landing to give you the most accurate information possible.
And Leah, let's go ahead and use that tool now. We have a screen off to the side here, and it looks like Athena is about 72 kilometers above the lunar surface, continuing to decrease her altitude over the next hour until firing her engine one more time for landing. Again, that landing time is expected at 11:31 Central Standard Time, 12:31 Eastern. The countdown clock at the top of your screen is counting down to that time, and we expect to remove the countdown clock approximately 2 minutes before the landing opportunity. Now, getting to this moment has been quite the journey, especially over the past 7 days in space since liftoff from Launch Complex 39A at NASA's Kennedy Space Center.
Athena lifted off at 7:16 p.m. Eastern Standard Time from atop a SpaceX Falcon 9 rocket on February 26th. Approximately 43 minutes later, Athena entered a translunar orbit, which is a direct shot at the moon. Over the next few days, Athena completed small engine firings to refine her trajectory before flight controllers commanded lunar orbit insertion on March 3rd to place the lander approximately 100 kilometers, or about 62 miles, above the lunar surface. For 3 days in lunar orbit, she has prepared to make her journey down to the lunar surface.
The journey to low lunar orbit took firing Athena's liquid methane and liquid oxygen engine 4 times, including one 7.5-minute burn to get into the moon's orbit. orbit. Over the last 24 hours, Athena has maintained her trajectory in low lunar orbit, waiting for suitable lighting conditions on the moon's surface to begin her autonomous descent to Mons Mouton, the designated landing site for the IM-2 mission near the south pole of the moon. And we did get to see some of that video, Leah. Rugged, but potentially the future of humanity down there on the South Pole.
Yeah, I can't wait to see what we find once we get there. And of course, this mission is called IM-2 for a reason. Just over a year ago, on February 22nd, 2024, Intuitive Machines became the first American commercial company to land on the lunar surface, touching down at the South Pole of the moon in Malapert A. The Nova C-class lunar lander was known as Odysseus. It broke a piece of landing gear as it touched down and tipped over, but still delivered and operated the payloads aboard for their intended duration. Now, due to lighting conditions at the South Pole, lunar landings in that area are limited for how long they can operate. The spacecraft gathered solar power for 7 days prior to shutting down and completing the mission. Our joint coverage today will follow Athena through her descent and landing on the lunar surface, carrying 10 payloads with her, including 3 from NASA. This mission is enabled under a task order with NASA's Commercial Lunar Payload Services Initiative. Here's more on how this project operates under Artemis.
Our moon. It seems so close in the night sky, but getting there is really hard. But what if there was a way to change that? Only a few nations have successfully landed on the moon. As NASA sends astronauts back to the lunar surface, this time to stay, we will need to send science and technology instruments ahead of time to lay the foundation for human exploration. To make this happen, NASA is helping establish a commercial lunar economy. For the first time ever, there will be commercial delivery services to the moon. We are enabling American companies to send our payloads to the lunar surface for us. These delivery services will expand our capabilities for exploration, radically increasing the amount of science we can achieve. This high-risk, high-reward initiative will invest in and leverage the entrepreneurial spirit of American innovation to launch a commercial lunar marketplace, advancing technology and exploration for all of us. With this never-before-seen streamlined access to the moon, we will be able to make novel measurements and develop technologies that scientists have long wanted to do on the lunar surface. And as this new industry matures, this commercial delivery service for NASA and other customers could expand beyond the moon to other destinations in our solar system. And we can learn to live on another world because we are explorers.
For more on how CLIPS contributes and fits in with our plan to land humans on the moon and Mars, let's head over to NASA's Antonio Jaramillo just down the hall.
Hey, thanks, Leah. Joining me is Joel Kearns, the Deputy Associate Administrator for Exploration with NASA Science Mission Director. Joel, we're getting ready for our second moon landing in less than a week. I mean, what an exciting time.
Well, it certainly is. I mean, we've had the launch of IM-2 on last Wednesday, and then very early Sunday morning, we had the successful landing of Glucose Mission 1 from Firefly. It's really, I'm over the moon at this point.
Yeah. You know, talking now about this specific mission for IM-2, can you tell us why some of the specific science and technology instruments were selected for this mission, and then also for the first mission for Intuitive Machines?
Yeah. So Intuitive Machines' first mission, NASA primarily selected scientific instruments. As a matter of fact, we left it up to Intuitive Machines to pick out which NASA scientific instruments that we had available for the moon they would fly on IM-1. But this mission is really different. It's not just Intuitive Machines' second flight of their Nova C model lunar lander, but this mission is almost focused exclusively on technology development payloads instead of scientific instruments. So the payloads that are on Intuitive Machines 2 will really test out and demonstrate new technologies that will be used in the future by scientists, by people that develop exploration systems, and by people that do operations in space. So it's got a really different character than IM-1.
You know, that's really fascinating. I can't wait to discover what we learn once we're on the moon. Now, Joel, can you tell us Why is it important that we have these different CLIPS contracts with the different commercial providers?
Well, for a number of reasons. One is that we, of course, when we buy a service, we want to be able to have competition so that we can get the best service at the best price the fastest we can. But even more than that, by having a number of different companies develop these CLIPS service landers, we're able to see the different strengths and the different entrepreneurial ways that they develop new techniques just for their lander, and it gives overall a much better suite of products for the United States to have. Also, one of our goals on CLIPS, in addition to carrying science and technology on the moon, is to generate a group of companies in the U.S. that are very good at landing things on the moon, so the U.S. government can buy that service, or other foreign companies or governments could also buy that service from the U.S.
Joel, thank you so much for joining us here today. Now we'll send it back to our hostess, to Leah and Josh.
Thanks, Antonia. We're following along with Athena's descent toward the lunar surface. I'll glance over at the viz, and it looks like she's continuing to decrease her altitude until powered descent initiation. She's right about 58 kilometers, but we expect PDI in approximately 36 minutes. That's powered descent initiation. That is a main engine firing that takes about 12 minutes. It's designed to slow Athena's speed in preparation for final descent moments before touchdown. The time of ignition for PDI is 11:15 a.m. Central Time, and that's 11 a.m., 12:15 a.m. p.m., Eastern. The entire landing sequence is autonomous, meaning the lander is in control of every milestone required for a lunar landing opportunity, although flight controllers do have the ability to intervene minutes before touchdown.
And completing a soft touchdown on the lunar surface comes with unique challenges because there is no atmosphere.
That's right. It's not quite Mars just yet, Leah. For now, it's an entirely different playbook.
Let's take a look at the IM-2 mission's complete trajectory approach and what Athena is expected to do on
people that are driven to build and fly and operate space equipment, and that's what we're here for. It's who we are.
Well put from Dr. Crane there, Leah. That is who we are, but let's take a closer look at what we've built.
This mission's Nova C-class lunar lander is named Athena. She's carrying 11 payloads, including NASA and commercial instruments to the moon, and including her solar panels, she's just over 15 feet tall. With the landing gear, she's just shy of 15 feet wide, and that's about the length of a standard car parking spot. The lander weighs nearly 1,500 pounds, with the majority of that weight at the base during landing, and it's capable of delivering about 220 pounds of payload to the lunar surface. And we've got a replica of Athena right here. So Josh, can you walk us through a few of the commercial payloads that are on board for this mission?
Pretty convenient placement, right? We
Yeah.
consider all of these commercial payloads to be pioneers on these early missions. Underneath the garage here, we have Lunar Outpost Map Rover, right, which is also connected to Nokia's 4G LTE system. That's their Lunar Surface Communications System. On the other side, we have another interesting bit. This one is Lone Star's data center, and the lander itself is protected by two innovative technologies from Columbia Sportswear, helping to protect this mission, making sure Athena makes it to her intended destination, Leah.
Athena and her payloads are expected to land on the Mons Mouton region of the moon. This is farther south than any lunar landing attempt ever.
And Leah, that is significant. Just like Earth, there are places on the moon that are like landing in an open field. The South Pole is a different story. This mission's landing site is more similar to landing on a small plateau in the Rocky Mountains, but that's where we think that there's going to be water in future exploration.
Well, to learn a little bit more, let's head to Antonio Jaramillo to learn about this landing site.
Hey, thanks, Leah. Joining me now is Ben Bussey, Intuitive Machines Chief Scientist. Ben, you know, both IM-1 and IM-2 chose the moon's south pole for its landing locations. Why specifically the South Pole?
So the lunar poles are interesting for both scientific and exploration regions. We know because of the moon's tilt that the craters near the pole are permanently shadowed. They never see the sun. So they're extremely cold, and we believe that water and other volatiles could build up inside those craters and in the polar region, and that represents a resource for future robotic and human exploration. And also the poles are sort of lunar incognita in that they've been relatively underexplored. If you think back to the Apollo era of exploration, that was all sort of equatorial, and so there's still a lot to learn about them.
Absolutely, and so can you tell us then a little bit then what's different then from both the landing locations of IM-1 and IM-2, even though they're in a similar area?
I would say there are more similarities than differences between the two landing sites. The poles are a challenging location in that when you look at the moon, you have sort of the dark regions that you see, which in Latin are the seas and the lakes. They're relatively flat terrain. But we want to explore the poles. The poles are what they call highland terrain, more rugged, low sun angle, which makes them challenging. And so IM-1 landed about 80 degrees south. It's also the location that the NASA with Artemis wants to send crew. So we're gradually working our way towards the poles. We're about twice as close to the pole with IM-2, about 85 degrees south, about 160 kilometers, 100 miles away from the South Pole.
And now, you know, you briefly touched on it, but can you discuss some more the challenges of landing in the South Pole?
Yeah, so I think when the team picks a landing site, there are really three parts to that. The first part, the most important part, is it has to be a safe landing site. The moon doesn't have an atmosphere. It has hazards. You can't avoid craters. And so you have to have the capability to avoid them during the final part. You also have to avoid the boulders. So the first step is going to be a safe landing site. The second part is, are you going somewhere where the instruments and the payloads that you're flying, can they achieve the science or the technology goals that they want to do? And that's one of the reasons we've picked the site that we have. And the third, one of the reasons also the poles are challenging, is unlike the near side of the moon where you'd see the Earth all the time and the sun would come up for 14 days and set, the sun is always on the horizon, and you play a sort of a game of orbital mechanics in that you need the sun and the Earth both to be up at the same time, and that changes every month. So the team has to take that into account as well.
A lot of things to take into account. You know, Ben, this is going to be Intuitive Machines' second lunar landing. How are you and the team feeling?
Oh, I think the best way to phrase it is nervous, excited. I mean, obviously the landing is exciting and scary, but we're very excited about what we hope the payloads will achieve. One of the payloads, the Hopper, is like a mini lander that can fly several kilometers. And one of the reasons the Mons Mouton region, it is one of the Artemis regions, one of the potential regions for crew. We're landing close to a small, permanently shadowed 200-meter crater. We've put instruments on the Hopper from Puli Space in Hungary. It's a neutron spectrometer. It'll measure hydrogen. So it'll be the first ever time we've taken a direct hydrogen measurement inside a permanently shadowed crater.
Very exciting times ahead. Ben, thank you so much for joining us. Now we'll send it back to Leah and Josh.
Thank you, Tony and Ben. As a reminder, Intuitive Machines' Lunar Lander is taking NASA science and technology demonstrations to the moon under the Commercial Lunar Payload Services Initiative. We call it CLIPS. Under CLIPS, NASA asks commercial companies like Intuitive Machines to provide lunar delivery services that advance capabilities for science, exploration, or commercial development of the moon. This flight will deliver 3 NASA instruments for CLIPS, including a drill suite called Prime 1 and a laser retro reflector array, or LRA. These NASA payloads will focus on demonstrating drilling capabilities, investigating resources below the lunar surface, and analyzing surface and subsurface volatiles. As we continue to descend toward the lunar surface, let's take a closer look at these NASA instruments. First is Prime 1, or the Polar Resources Ice Mining Experiment 1. Prime 1 is a collection of 2 instruments that complement each other's work: the Trident Drill, which stands for the Regolith and Ice Drill for exploring new terrain, and MSOLO, which stands for Mass Spectrometer for observing lunar operations. The Trident drill will extract lunar soil, also known as regolith, up to 1 meter or approximately 3 feet below the surface. MSOLO, the mass spectrometer, is designed to analyze the composition of that sample for water and other components. In addition, MSOLO will measure the composition of gases released near the drill activity. This technology instrument will help demonstrate drilling capabilities that will help scientists understand the on-site or in situ resources that already exist on the moon.
NASA's next payload is the Laser Retro Reflector Array, or LRA. It's a collection of 8 retro reflectors similar to the reflectors on your bike that enable precision laser ranging, which is a measurement of the distance between orbiting or landing spacecraft to that reflector that we have on Athena. LRA is mounted on Athena's top deck, so when a laser hits it, it reflects light back to the orbiting spacecraft. And LRA is a non-powered or passive instrument that's intended to function as a permanent location marker for decades on the moon.
Another common theme you'll find among the NASA payloads on IM-2 is helping to demonstrate technologies and our understanding of that lunar landscape that could very well improve operations for landing on the moon in the future. The technology on IM-2 will provide valuable data to help us better understand the moon's surface and allow us to gather insights that will shape the future of lunar resource utilization.
And Leah, using CLIPS as a springboard, Intuitive Machines really based that innovation off of that. We designed and developed a complete lunar program to help support CLIPS and carry out an essential directive underneath that initiative that calls for the commercial development of the moon. That opportunity for Intuitive Machines expanded services outside of NASA payloads, opening doors for commercial industry to achieve those lunar ambitions.
On IM-2, there are 8 commercial payloads flying alongside NASA's Prime 1 drill suite and Laser Retro Reflector Array.
That includes commercial payloads from around the world, like Lone Star's data center, a rover from a company based in Japan called Diamond, Columbia Sportsmare, and a couple more we'll touch on here just in a second.
Absolutely. Some additional payloads on board Athena are largely driven by NASA's Space Technology Mission Directorate. These are NASA-sponsored experiments, but developed by private companies. These are also called tipping point awards. These tipping point initiatives are valuable to the lunar economy as we move toward returning to the moon.
And as part of NASA's Tipping Point initiative, Intuitive Machines developed its micronova hopper. We call her Grace, and she's a rocket-fueled drone designed to hop across the lunar surface and into a crater, a place humans and rovers are unable to access. After Athena touches down, Grace is designed to fire her 3 hydrazine engines to lift off from the lander, making her initial landing not too far from Athena. And over the next several days, Grace is expected to make 4 hops, and the 4th hop, Leah, into a crater called Crater H. We intend to rename that crater perhaps with a little bit more personality.
Can't wait to see what you come up with. NASA is interested in what Grace may uncover in the crater because there are regions inside craters that never see light from the sun, and that means they remain extremely cold and could have volatiles like water.
And to detect things like water, Grace is equipped with 2 commercial payloads. One of them is a water snooper from Pulley Space, and another is a lunar radiometer from the German Aerospace Center. We expect Grace to take readings in the shadow crater for about 45 minutes before making one final hop out of that crater to transmit her data back to Athena.
And Grace isn't alone on her mission. She's getting help from another NASA tipping point. To talk about these payloads and the Space Technology Mission Directorate's role in bringing these game-changing technologies to reality, let's send it to NASA's Antonia Jaramillo.
Hey, thanks, Leah. Now joining me is Nikki Werkheiser, Director of Technology Maturations for NASA's Space Technology Mission Directorate. Nikki, can you tell us a little bit more about NASA's Tipping Point initiative and how it's being leveraged on this IM-2 mission?
Of course. So the tipping points are really kind of the heartbeat of what we do in space tech. The whole idea is that technology really enables science and exploration, our commercial ecosystem. So we really want to have, just as much as we want to have exciting new technologies, we want to have new exciting ways to partner and be very agile and really leverage each other's strengths from the government and the commercial side. So the tipping points allow us to do that. So with the tipping points, industry, the companies that we're working with, put contributions in. They have internal research funds and development, and then the government puts money in. So we're true partners in creating these capabilities.
Now, specifically on IM-2, why did NASA decide to invest on Intuitive Machines' Micronova Hopper, or GRACE, and then also the Nokia Lunar Surface Communication System?
So I'm glad you asked. So we have something called the Lunar Surface Innovation Initiative, and it was started in about 2019, shortly after Artemis. The whole idea there was, in order to do anything on the moon, you're going to have a set of capabilities or technologies that everyone is going to need. Just your basic infrastructure, if you will. So things like power and surviving, the dust and the environment you're in. But two of the key areas that come up over and over again, of course, are autonomy and robotics and mobility, being able to get around. We all know that there are places on the moon that are more treacherous than others. It's a pretty rough environment. So we have permanently shadowed regions, which you've heard about earlier today that we want to get into. The hopper can do that, right, and get that data and show us what's in there. There's where we think we might have some water or ice. For the communications, that's a no-brainer, right? Every time I talk to, whether it's a second grade class or my grandmother, then they would, when we have our cell phones, when am I going to have my phone on the moon? You have to be able to communicate. Whether you're in your rover and traversing, whether you're in your suit or in your habitat, you have to have a way to be able to communicate. So it's very important that we get this communications established.
And aside from making sure we have communications on the moon, I guess how does NASA determine what other technologies are important to demonstrate on the lunar surface?
Right, so this has been a lot of fun because what we really do is look at the larger, I'm going to say, ecosystem of both what NASA wants to do from an architecture perspective, but also from establishing a commercial ecosystem on the moon. So there are certain capabilities that you're going to need, those infrastructure items, if you will. So when you think about living and working somewhere like the moon, I don't know about y'all, but if I go to Walmart, if I go to Florida, I'll have to stop at Walmart and buy my flip-flops, right? You have to prepare for a lot of different things that could happen. So you need that basic infrastructure so you can be more independent from Earth and live and work. So things like power. I mentioned the dust. We learned in Apollo that the dust is very abrasive and very hard on your systems. So we have active, passive, and operational ways to control that. You notice I say dust mitigation, not solutions, because you have to mitigate it. Being able to rove around, being able to have communications, in situ resource utilization, which Prime will be looking at, on how we can use the natural resources where we are instead of being totally Earth dependent. So doing those studies, understanding kind of infrastructure that everyone is going to need is how we pick and prioritize.
So definitely a lot of important technologies. Yes. Nikki, thank you so much for joining us and speaking with us today. Now we'll send it back to Leah and Josh.
Thanks, Tony and Nikki. Here's a deeper look into how the Nokia tipping point will work and the benefits for future missions.
On Earth, a cellular network has many components: base stations, radio units, and a core network that manages the connection between users and the network. Nokia's technology miniaturizes and integrates all of these components into a single network in a box.
This is Nokia Bell Labs Network in a Box that you can hold in your hands. It contains every single component that make up a 4G LTE network. Scaled down to this size, weight, and power, we could install it onto the Intuitive Machines Nova Sea lander along with specially designed antennas. Every gram that we send to the moon matters. While compact, the system also has many redundancies and fail-safes, allowing it to recover and heal itself. We also overhaul the system software to minimize the impact of ionizing radiation that would normally cause sensitive electronics to malfunction.
The network links directly to devices in both the Lunar Outpost Map Rover and Intuitive Machines Micro-Nova Hopper. For the mission to succeed, this network must be fully autonomous. It must deploy and configure itself once on the lunar surface. As the lunar rover goes about conducting experiments, and the hopper goes deep within a crater, the network must also constantly make adjustments to ensure it maintains connectivity.
This is an uncrewed mission. There will be no human technician to tweak or repair the network if something goes wrong. Achieving that level of autonomy was a monumental task to undertake. Working with NASA's Space Technology Mission Directorate, Nokia plans to test the first cellular network on the moon. Success will have implications far beyond this important mission.
In addition to the NASA payloads and tipping point initiatives, Lunar Outpost has another mission objective. Not only will the Lunar Outpost carry the Nokia tipping point demonstration, it will also collect lunar regolith, also known as lunar soil. Lunar Outpost and iSpace have contracts through NASA's Space Operations Mission Directorate for regolith collection. When completed, the companies will provide imagery and location data of the collected material and transfer ownership to NASA.
Now, the purpose of this effort is to show that transfer of ownership from private to public. Lunar Outpost Map Rover will be on IM-2. This rover will also carry the Nokia tipping point demo we just mentioned and traverse the moon. And the company's lunar surface communications system that's from Nokia will demonstrate proximity communications between Athena, Lunar Outpost rover, and the hopper.
The Lunar Outpost Map Rover aboard the IM-2 mission will also carry a technology from the MIT Media Lab Space Exploration Initiative called AstroAnt, which was tested through STMD's Flight Opportunities Program. To change the pace of space, the Science Technology Mission Directorate's Flight Opportunities Program works with industry flight providers to rapidly demonstrate promising technologies in reduced gravity and other relevant environments.
And Leah, we're just about 12 minutes from Athena starting her final approach to the lunar surface, and things are moving forward as going into an intense 11-minute main engine firing towards the lunar surface. And to this point, Athena has traveled over 700,000 kilometers up on the Viz over 8 days for this final, very risky maneuver.
Yeah, risky is right. It's no secret that landing on the moon is challenging. Countries around the world have attempted this incredible feat, with some being successful and some not. Of course, the United States has landed on the moon many times, most notably during the Apollo program. But today we're looking for the third landing by a U.S. commercial company enabled under NASA's CLPS initiative. Ahead of these important milestones, let's discuss the challenges of landing on the moon through CLPS. Take a look.
Landing on the moon is hard. We're going back. Under this Artemis program, we're going to be sending humans to the moon for the first time since Apollo. So ahead of humans, we want to get up as much science, exploration, and technology experiments as possible.
So CLPS starts facilitating a lot of the early science, the things we want to learn before we even send humans. CLPS stands for Commercial Lunar Payload Services, CLPS.
The services part is the key element. Ordinarily, when NASA delivers a payload to the surface of the moon, they do it with a commercial partner, but NASA controls the building of the vehicle. Now, we're buying the service of delivery of our lunar payloads to the surface of the moon.
It is a delivery service, akin to a delivery service that you'd have here on Earth.
NASA will provide payloads to a commercial company. They decide how to get it to the moon. They have to develop their own lander, but they also have to manage the entire end-to-end mission.
It's meant to provide affordable, rapid, frequent access to the lunar surface through American companies.
We're funding different companies.
We have commercial companies that are competing to win task orders to deliver our payloads to the surface of the moon.
One of the goals when we started CLPS was to help establish a lunar economy.
Somebody has to do it first, and then it becomes commercially available. Then they're able to crank them up. Then they're able to make it more affordable. And so the lunar surface is just the next frontier for a commercial environment.
But we had to acknowledge up front, all the way through the highest levels of the agency leadership, that some of them will fail. These missions may not be as successful as a traditional NASA mission.
We have accepted the risk that going through this innovative approach with these commercial companies, that there could be some failures. Some of them are new companies. None of them have ever successfully landed on the surface of the moon. So they're going to learn lessons.
We need to give our vendors the opportunity to learn.
And so that'll help ultimately buy down our risk as these companies learn, okay, what does it take to actually build up the lunar lander, integrate payloads, get to the lunar surface and land safely.
They've been able to demonstrate that they have very, very good technical depth and the ability to design and execute missions. We're willing to take more shots on goal. And we aren't risking human life. And in the big picture, if we're flying missions at 1/10 of the cost of a NASA mission and we fail 2 of them, we still get 8 missions for that same price.
Even with 1 or 2 or 3 failures, this is still a very economical proposition. It's a risk posture which is more risk tolerant than NASA is accustomed to. There's not a single one of these companies that's willing to bet their mission on a coin toss. Every one of them is doing what they can in order to have the most successful mission possible. But the important thing to realize is that risk tolerant does not mean risky. And the rewards are a long-term ability to get payloads to the moon inexpensively, frequently, and rapidly.
We want science, so we can then put more of our resources on even more science, exploration, and technology payloads and get more of a return on investment when we get to the moon.
CLPS provides tremendous benefit across the scientific and economic communities.
So there's a lot we'd like to learn about the moon to help human habitation and prepare us for missions to Mars and beyond.
So the moon is the first step.
We are coming up on just about 22 minutes from Athena's planned lunar landing attempt. Let's take a live look into Nova Control. Josh, can you tell us what's going on right now inside your Mission Control Center?
Well, flight controllers are all monitoring Athena's flight data in near real time. That means Athena is sending data from nearly 250,000 miles away to ground stations contracted by Intuitive Machines across the globe and into Nova Control. The mission director and landing system experts are looking at a screen called the Deorbit Descent and Landing, or DDL screen. It's used primarily while Athena orbits the moon through to landing. That same data flow is being interpreted through a video game engine to create what we call the viz that you see on your screen right now. Well, we have made some improvements to increase the fidelity and reliability of the viz. We expect to keep it up for you during the landing, although the last few seconds may be an estimation of what's happening, as Athena may lose communications contact, particularly when she pitches over right before vertical descent.
Right now, looking at the viz, it shows Athena approximately 15 kilometers above the lunar surface, so we're getting close. Now, when the lander makes it down to about 10 kilometers, we expect Athena to continuously fire her main engine, throttling down until softly landing on the lunar surface.
And Leah, that final burn is called Powered Descent Initiation, or PDI. Athena must slow down by about 1,800 meters per second, which doesn't mean too much until we typed it into Google. That's about 4,000 miles per hour. That's because she's approaching her landing site coming down from orbit, so she has a lot of lateral speed. You can think of PDI like hitting the brakes on your car in order to make a safe turn. But in Athena's case, that turn is moving into a vertical upright position to start descending down to the lunar surface. PDI should be starting here just in about 6 minutes, I believe. Leah?
The teams here in Nova Control have been working diligently over the past 7-8 days to take us this far. Now, again, only 15 kilometers above the lunar surface. We're following the countdown to Athena's landing attempt, but for now, we're heading back over to Tony Hadamia, who is standing by with NASA's acting administrator, Janet Petro. Tony?
Thanks, Leah. It's always an honor to be joined by NASA leadership, and joining us now is Acting Administrator Janet Petro. Janet, we're getting, 20 minutes until landing. How are you feeling?
I'm feeling super excited. I got a little nervous, fingers crossed, toes crossed, but looking forward to it.
Absolutely. I have everything crossed too. Can you tell us a little bit more about the challenges of landing on the moon, especially for these uncrewed robotic spacecraft?
Yeah, so even, you mentioned these are uncrewed, but even back in the Apollo days, the 7 times we landed on the moon, it was very, very challenging, required a whole bunch of simulations and demonstrations to get that right. And so for the uncrewed, so each lander is unique. So each is developed differently. And the harshness of the environment with no atmosphere, the dust that's going to spring up when it lands, all these conditions make it really, really hard to do it right and get it right. And so one thing I found from the Firefly from last week, all these companies know how hard it is. Their own technology, they've got to have precise propulsion and navigation systems to get them right down on the surface, and it's all automated. You know, we're 238,000 miles away from Earth, so there's no real-time control, so that the systems have got to work perfectly together. So these companies, that they support each other, and I was started to say we were at Firefly, and several of the other companies sent them in coffee and donuts because they know how stressful it is for the team as they're coming in for a landing to make it, and hopefully it'll go right. But it is really, really hard to make sure that all the systems are working seamlessly and perfectly, and that as they get closer and closer to the lunar surface, that the rugged terrain that they're about to land on, it all works out. And the South Pole is increasingly challenging with the very, very deep craters that are there. The low level of light and the angle of the sun make that even more challenging. So it's harsh. It's harsh.
It absolutely is, and it's just even more impressive when the teams then are able to land, well. Janet, can you tell us how these commercial then lunar flights that are part of the agency's CLIPS initiative, how are they helping us then in our own Artemis missions when we send humans back to the moon?
Yeah, so I consider them part of the way bigger Artemis missions as we're going back to the moon and then on to Mars, that we talk about all the time. And so CLIPS, the Commercial Lunar Payload Services, I just think it's a brilliant partnership between NASA and innovative companies to come up with their own concepts and ideas and help put forth science and instruments earlier than we're going to be able to get humans on the moon. And we'll be able to learn a lot from these instruments and payloads that we're deploying. Things like, the water ice. Maybe we can find some water ice. Different roving mobility techniques. Of course, looking at all the lunar resources and the drilling, drill baby drill that we're going to do on this mission. So all of that we're going to be able to apply to Artemis when we get humans back on the surface of the moon, and then as we go out to Mars. And again, I think CLIPS is a brilliant partnership. And I mentioned, I believe this administration talks about America first, and I think the way we can do it is by bringing along industry and really dominating the space, whether it's low Earth orbit, whether it's cislunar, or whether it's on the surface of the moon. I think we will continue to push boundaries and make sure that we are first and retain leadership in space.
A lot of exciting science ahead. Janet, thank you so much for joining us today. Now we'll send it back to Leah and Josh.
Thanks, Antonia. It's time to buckle up, space fans, or lean forward in your chair. We just heard the call out for 90 seconds for time of ignition for PDI. Let's go ahead and open up those operational channels so that folks at home can listen as we go in towards PDI, Leah. That's a braking burn coming out of orbit, trying to slow down about 4,000 miles per hour.
Yeah, PDI stands for Power Descent Initiation. So this is really that final commitment that we are coming in for landing. And everything is really going to happen in rapid succession after this 11-minute burn, now just 60 seconds away. The rest of the sequence is only about 2 minutes to touchdown. Can you break that down for us, Josh?
That's right. It's going to be rather quick after we get through this PDI maneuver. You're going to hear things from call out for 45 seconds. After PDI, we'll have pitch over, HDA, vertical descent, and then landing operations. We're just now inside about 30 seconds, standing by for that time of ignition for PDI. 30 seconds.
And with 30 seconds, we are now 13 kilometers above the moon. Again, we're going to bring it back down to 10 and start that burn.
We might be listening.
AFM is in exec mode.
I was just about to say we're listening for exec mode here.
15
seconds.
RCS settling burn.
Settling burn. That's our attitude control system.
Ignition commanded.
Ignition and main stage.
All right, let's go ahead and start our stopwatches here. Leah.
Cameras are running.
We'll be listening for that max thrust.
AFM mode is breaking 1.
Chamber pressures look nominal.
Good calls. They're not going in at 100% here, Leah. They're
Good
going in about 90% in case they need a little bit more oomph on this braking burn.
Again, this is about
Good control.
an 11-minute burn, but the engine does not cut off at the end of this burn. It just continues to throttle down until we land softly on the lunar surface.
And we're listening in to hear some good confirmations of data. If you hear good confirmation of data, that means that that data is making its way to the viz, what you're watching right now on your screen. We do expect to lose some of those communications, especially during that pitch over maneuver at the end of PDI. That's when the lander will be changing its attitude and maybe those antennas aren't pointed directly back to Earth. It's something we expect, something we plan for, but one thing that's unique to the lunar south pole is what's called multipath, and that's when you have radio waves reaching their intended destination back at Earth after they're taking a different route, maybe bouncing off a crater or a ridge. So we do expect less than optimal radio signals on the surface, but that's something we have to plan for, and it's something that's reflected inside the viz here. So if the viz does lose communications, it's going to continue moving in its last estimated vector. So folks at home, you might be seeing the lander touch down on the surface, but the ultimate call of confirmation and what is happening is going to come from that mission director seat. You see it in the small box on the bottom right hand of your screen. That's Dr. Tim Crane in the mission director seat today.
Coming up on 1 minute and 45 seconds since the start of the burn, again, an 11-minute burn using the main engine aboard Athena. And if you're watching the viz and it looks like Athena is traveling parallel essentially to the lunar surface, that's because it is. This is a braking burn. Confirmation 2 minutes in, and a better picture on the viz that shows just
Chamber pressure still nominal.
Continuing to get good calls, but the next step will be pitch over. So during that pitch over time frame, Athena will begin to upright itself and prepare to descend down to the lunar surface and also activate HDA, or hazard detection and avoidance. Can you break that down for us too?
Yeah, we touched on this at the top of the show, Leah. We are going in at about 450 meters for PDI versus our originally planned 400 meters, and that's because we had some uncertainty and variability within the recent landing measurements, going in about 50 meters higher, allowing those flight controllers to manually confirm and screen alternative measurements. But we do expect that our estimated landing time will stay closer towards that estimated 11:30 Central Time. That's 12:30 Eastern. And right now we're standing by, just about to hit 3 minutes into this burn. We're listening.
3 minutes in.
There it is. How about that? And we're listening in to hear for things about how many kilometers uprange we may be. We know this braking burn will continue to happen until about 2 kilometers from our intended landing site. Now that intended landing site is where Athena...
Still processing good depause.
Hey, that's a good call. All right, folks at home, that depause is that delta position, meaning the lander is taking pictures in flight, and she's comparing those two pictures together to determine how much have I moved and figure out how fast did I get there in order to affirm that Athena's going in the right direction, making the right moves going forward. Another good thing about depause, we're getting good comm. So on your screen at home and you're looking at the viz, you're looking at, what is this, about 16 meters. That may be off, about 16 meters. We'll stand by for a call out to confirm maybe altitude as well as distance to the landing site. But if they're getting good depause, they have good comm. Again, we do expect, plan, and train for a loss of comm right around the pitch over time frame, and maybe also as well as we descend towards the lunar surface, making sure that our radios and antennas are in the right config.
490 seconds left in the burn.
490 seconds left in the burn. That's code for, we've been burning for about 4 minutes, Leah. We'll stand by to try to get some more data and call-outs here, maybe some kilometers up range, as well as the mixture ratio, trying to figure out the vehicle's performance, that mixture of liquid methane and liquid oxygen going into the engine. Let's take a second and listen in to flight controllers here.
GNC 174 acknowledged.
It's a different mode inside of the guidance, navigation, and control software called out from Michaela Landivar, if I'm not
Chamber
mistaken.
pressures and temperatures still nominal.
Nominal temperatures. This
450 seconds left in the braking.
450 seconds left in a braking.
5 minutes in.
Code for 5 minutes in.
Again, this is a braking burn, the powered descent initiation, really committing us to our final descent. Earlier this morning, we had the DOI, or the descent orbit insertion, which got us out of lunar orbit itself. And since then, Athena has been completely autonomous. So Josh, is there anything right now that flight controllers can still command on the spacecraft?
That's a good point. I mean, there is an autonomous process that is bringing Athena from descent orbit insertion, triggering powered descent initiation, and then through to the lunar surface. Flight controllers do have a few options to manually intervene. We talked about allowing a little bit of extra time with that additional 50 meters for
400
PDI.
seconds left in braking.
400 seconds left in braking. We're almost up on 6 minutes inside of this burn. But that extra 50 meters is allowing flight controllers to manually confirm and screen alternative measurements, as we did have a little bit of uncertainty and variability with recent landing measurements. By my count, we're just crossing about 6 minutes, Leah.
That means we're
GNC 175 acknowledged.
Another guidance, navigation, and control mode call out there.
We are over halfway into this 11-minute burn using the main engine on Athena.
AFM is in braking 2.
Braking 2, progressing through that PDI count, Leah.
350 seconds left in braking.
350 seconds left in braking, just crossing over the 6.5-minute mark since PDI, powered descent initiation. This is one continuous burn from PDI all the way down to the surface.
VFM mode is DPOS only.
All right, we're still processing delta position. Those are camera measurements the lander is looking at and making decisions. One of those decisions will be using hazard detection to fly to an intended landing region and then autonomously make those decisions of a safe site, whether that's safe from boulders or steep slopes. We'll hear those call outs after we pitch over. You'll hear HDA, and that's what we're listening for to figure out where those hazards are and choose a new landing site.
Now over 7 minutes into the burn, this braking burn,
300 seconds left in braking.
specifically 300 seconds left, this braking burn.
Engine is still healthy.
And great confirmation about the engine itself. That engine is bringing
GNC
us
176 acknowledged.
Engine is bringing us from about 4,000 miles per hour to eventually a soft about 1 meter per second, or about 3 feet per second landing.
And I'm catching a little jitters watching the viz here, so I think folks at home will be seeing the same thing. Remember, this is data being streamed down from a lander that's braking about 4,000 miles per hour, trying to feed that data back 250,000 miles away.
TAL is ebb now at 5 dB.
Just to enjoy a little view.
8 minutes elapsed.
Camera's now in braking 2 mode.
We are still inside of PDI, braking 2 mode.
250 seconds left in braking.
So we cross over 8 minutes into this burn.
Again, about an 11-minute burn. We don't expect the engine to reach full 100% thrust. It's really a throttled approach. This engine is designed to continuously burn in throttle all the way from power descent initiation, which began 8 minutes and 30 seconds ago, through touchdown. This approach is very similar to what we saw for the Apollo descent modules as well.
And it makes a lot of sense. If you go in at 100% and you need a little more, there's nothing left to give, right? We want to come in nominally around 90% and then have a little bit of room to play if we do need to increase the speed of which we're slowing down. You'll hear folks maybe call out the rate of acceleration, but in this case, for us, that's deceleration.
9 minutes elapsed.
Crossing over 9
200
minutes.
seconds left in braking.
Yes, just a couple of minutes left in the braking burn, so another look forward to that rapid succession of events that'll come immediately after braking is complete. We will see pitch over begin. We'll be using those 4 RCS, or reaction control system thrusters, at the top of this spacecraft to reorient Athena before its a final approach, vertical descent, and terminal descent.
And all of those after PDI, Leah, that you just called out, we're expecting those to happen rapidly. We can kind of sit back and let flight controllers really get into what's happening. We'll take a few chances in between to help. There's a LOS on one of the radio systems. Again, expected as we get in towards our pitch over maneuver. Some jitters on the viz.
Chrysonics still showing good data.
That's the second radio. So the first one,
Good data on Chrysonics.
the first one we heard a loss of
GNC
signal.
177 acknowledged.
The second was a confirmation that the
10 minutes
second
in.
radio, we still have signal. So it's good signal, good data, good viz, and we're watching the show here along with the folks at home.
10 minutes into the burn, so expecting just about a minute more until the end of this braking maneuver.
We expect and plan for pitch over just about 2 kilometers away from the intended landing site. That gives Athena a little bit of time to pitch over and start looking forward using her navigation sensors to detect different hazards, as well as her altitude, to lower down to the lunar surface at approximately 1 meters per second if all goes towards plan. There's LOS as we approach our pitch over. All right, we're approaching 11 minutes into the burn. Local time is 11:26.
AOS on Quasonics.
11 minutes in.
11 minutes in, we heard another call out that we're up on Quasonics. That's our radio system. It's 11:26 local. I'm looking at a pitch over time at 11:27 in about 52 seconds. So we are coming up over into the pitch over, where we expect to have some loss of comms. Earlier we talked about multipath. That is very unique to the lunar South Pole, where our radio signals are using multiple ways to get to the same destination, whether that's from bouncing off the harsh terrain or some different polarity issues down there on the South Pole. We expect to have a weaker than normal signal, but we still want to make sure we get that confirmation, Leah. As part of that confirmation, we're going to safe the vehicle, figure out the status there, and then start working on pictures after everything's safe. Maybe around 2 hours after landing, we can cherish that photo.
LOS on Quasonics.
There's that loss of signal on one of the radio systems. We approach 12 minutes into PDI.
Again, the engine will continue to fire, albeit it will continue throttling down as we approach the lunar surface. And a reminder, the Viz is a simulation based on flight data, but if we do lose contact with the lander, which can be expected based on the conditions at the lunar South Pole, we will continue to see projected data on this visualization.
And we're approaching G as in ground to 2 minutes. We expect to drop this clock here in 2 minutes and take all of our commands from inside of Nova Control. The bottom right hand of your screen, that's Dr. Tim Crane, our co-founder and Chief Growth Officer, also sitting in as Mission Director for landing this IM-2 mission. Standing by for the latest information. Let's wait one.
Quasonics AOS.
HRN, HGA, HGA2.
Thales AOS.
60 seconds left in braking.
60 seconds left in braking.
In approach. Landing site selected.
Engine at idle.
11 meters cross range, divert.
Quasonics LOS.
There's that loss of signal over pitch over. Stand by, see if we regain that signal. Remember, folks, the Viz that you're watching at home is an estimation of data. It's doing its best. That's a lot of data coming from really far away. All commands and all confirmations come from our mission director at the bottom right hand of your screen.
Again, we are standing by, monitoring the Viz just as you are at home, along with Nova Control.
We are approaching approximately the time that we estimated Athena would touch down on the surface. We did hear a call out for a Quasonics LOS. That is our radio system, something we expect to happen at pitch over. That's prior to a vertical descent and terminal descent. That latest
Comment,
data
how are we doing on signal?
is what you're seeing on the Viz. Why don't we go?
We currently are getting our uplink through Hemi 2, and we have a healthy AGC value, so our uplink is coming in strong for Talas. And then for our downlink, we have a strong EBNO at 17 on Green Hilly, and we are currently not seeing our Quasonics. So we are in Quasonics LOS.
All right, that's a
See our signal strong on the spectrum for Talos. I'm not seeing our Quasonics on our spectrum as of yet.
FM, what mode are we in?
Approach 17 is the last we've seen.
All right, so that's up on one radio, and they do have a loss of signal in the second.
Fido, I'm looking at the SenseXL. Do you see the SenseXL reading?
Let me look.
That's a mission director detecting CF
I am
lander.
seeing a SenseXL 1G.
So that was the mission director, Tim Crane, trying to figure out what is the vehicle sensing. It has two inertial measurement units on board. You can think of those as your inner ear. So when he's asking what is the sensed acceleration, that's what he's asking for, is what is that inertial measurement unit, that inner ear, detecting as far as acceleration.
Again, as we've mentioned, the Viz here is just an interpretation of landing.
Yeah, let's go ahead and stay on Nova control. Looks like the Viz is hovering. We can't.
Prop, what are you seeing on the engine?
The engine is still in idle at min thrust. We are still seeing chamber pressure.
So we're getting good data. We heard that we have one radio up, one radio loss of signal. We just heard that we
I'm
have.
seeing guidance to solution for time to go as increasing. It's indicating to me that it is the onboard nav state is not decreasing in altitude.
The good news, the HRN laser is now ready to fire.
So we heard that we have one good radio sending down data, one that has loss of signal. We have prop.
Standing by with a manual command for landed ops.
Yep.
No recommendation at this time.
Yep, we have prop telling us that we have good data. That was someone just commanding. We heard exec mode to go into this firing mode, and someone standing by to get into our landed ops mode. I'll wait for Dr. Crane to confirm here. But if we're pulling down data, we'll see how this goes. Looks like Tim's about ready to jump on the loop and sort out what we saw on the Viz versus what the folks inside of Mission Control are seeing on their monitors. It's a good reminder, too, this public channel that we're listening to here in the studio, Leah, and what people are listening to at home, at the landing party at Lone Star Flight Museum.
All right, folks. I'm showing that we are sensing lunar acceleration. So we're on the surface. Let's evaluate.
All right, let's continue to evaluate. I hear we do have a picture from a portion of the descent. Is that right over there? All right, so that's a picture during braking, about 10 kilometers up from the lunar surface that we do have while we wait for a little more information.
We can confirm the engine is still running and therefore needs to be upright. If we were in a different configuration, the engine would have snuffed.
Okay, so we have confirmation. I believe that was from Con that says the engine's still running. This picture you're looking at, the 10 kilometers up during that braking burn, that powered descent initiation, that long burn that brought us 4,000 miles per hour braking burn. Incredible shot.
Yeah, that's what I'm saying as well.
All right, there's another view there. Looks like from this panel, we're looking at the garage. So that's Lunar Outpost Map rover inside of that square right there, Leah. And this looks like it's probably about the same altitude, maybe about 10 meters above the surface. And one more here for everyone. It's about the same altitude there, maybe a little bit more exposure, but these
camera's still running in HRN mode.
These photos came down for us just a few moments ago. Wanted to share those before we jump back into mission control as flight controllers are looking at this dynamic situation and learning.
Yeah, go ahead and put us in landed ops. It looks like we're down. We need to evaluate that situation, and I'd like to get a picture.
As they say, picture it didn't happen.
Hello,
so Dr. Crane's onto it right there. A couple things here, Leah.
FM 3402 was acknowledged. AOS on Thales.
What we're hearing in our ears and what folks at home are listening to are not the only channels
Check your systems.
that mission
Engine
controllers are working on. It's an engine shutdown notice. We'll see what comes out of this. But they're all on different loops having separate conversations, so all the information that we have, that folks have at home, isn't necessarily the exact vibe inside the room. So we'll stand by and listen in to see what we have here. I did hear Dr. Crane call out that they are getting readings for lunar acceleration.
To the post-landing court procedure.
All right, Spark, I'm going to start shutting some stuff off as soon as we can.
Copy. Can you meet me on my loop, please?
Feed lines are inerting.
All right, so if we have enough data to be inerting feed lines, that means the engine's no longer running, and it's a state to bleed off that extra pressure. This is part of that safing bit that we talked about earlier, Leah. Looks like our CEO, Steve Altimus, just stepped into the room. That's in the bottom right hand of the box here, talking to the mission director, Dr. Tim Crane. He just called out telling Spark to turn some things off. That's because we need to remain in a power positive state, Leah, getting that top deck solar array into a spot where we are able to charge, but sometimes you have to turn a few things off to make sure that you're charging and not just burning through that power. All right, by my countdown clock, it's been about 22 minutes since we started that PDI, Leah.
And again, we were anticipating landing at about 11:31 a.m. Central Time, 12:31 p.m. Eastern Time. It can get tricky with communications on the lander when you're in a...
Prop, do we have insight to tank pressure if we turn off the Mogies and the Iggies?
We would, yeah.
All right, that's code for the...
If you turn off Mogies, then we cannot inert or vent the tanks.
Yeah.
We can bring them back up though, right?
Yes.
How are my pressures?
They're low at this time.
Okay, turn off the Mogies and the Iggies. Going.
Could we turn everything off except the vent valves?
Yes.
That would be everything except MV103 and MV303.
All right, all this activity is regarding the lander's propulsion system. They're going through deciding on how to vent it. We heard two things there, Leah. We heard Mogies and Iggies. That's our motor engine gimbal system, right? And our Iggies are igniter. So they're working through the process of safing this engine. At the top of the show, we talked about the priorities after touchdown, and being safe was first, followed by pulling down some health status information, and then images. And then just about 3 minutes ago, we heard Dr. Crane go ahead and say,
FM 3403 acknowledged.
We'll prioritize images. It's just about 9 minutes after the expected landing. So let's hang tight and continue to watch this problem and challenges unfold inside of mission control. Each one going through, finding this challenge, each one getting solved here. It sounds like they're still working through venting the engine system.
Let's power off the Quasonics until we get a handle on what antenna we're going to pipe it through.
Copy. Quasonics is currently in idle mode.
Good enough, thank you.
Quasonics, that's our radio. There's two radio systems on the lander. It sounds like when we talk about that vehicle health status, we heard some things for prop. Vehicle health status includes being in a power positive state.
Spark 636 acknowledged.
So we are communicating, commanding the lander, and getting acknowledgments back that the lander is behaving as expected. So putting those things together while we wait for confirmation from Dr. Crane. We have an engine that is shut down. We are venting the engine.
Spark 637 acknowledged.
We are getting acknowledged commands from the lander. Standing by for confirmation from Dr. Crane.
And just a recap of some of the timelines so far today, we had power descent initiation start about 25
FM
minutes ago.
3406 acknowledged.
Power descent initiation is the braking burn that really committed us to coming down to our landing site today. We were targeting landing at about 11:30 a.m. Central Time, so about 10 minutes ago now. Again, still just standing by for some confirmation from the teams in Nova Control, and hopefully a picture that shows the status of Athena on the lunar surface. Landing site today is Mons Mouton. It is the furthest south target for any landing up into this point.
And pretty credible images we just went through. You know, for those to come down during
Spark 638 acknowledged.
During that landing sequence, showing during that deceleration burn, just about 10 meters, I believe that was, over the surface for those images. See who we have in there. Yep, down towards the bottom right-hand side.
Spark 639 acknowledged.
Of your screen, we keep hearing those acknowledgments of the vehicle receiving our commands as we stand by for the real deciding factor here. Never a dull moment, Leah.
We did hear that they were going into
Spark 640 acknowledged.
Commanded landed ops. So can you walk us through some of what that means? I know that includes safing the engine as well.
Right, so there's different modes that we need to command, right? At the beginning of PDI, we hear the command for exec mode, all right?
Spark 641 acknowledged.
That's executing the burn maneuver, right? When we switch over into landed ops, it's a different setting on the lander in order for us to go through those steps, safing the vehicle first and foremost, that liquid methane, liquid oxygen engine.
Yep, bring it down. Also, FM, I'd like a recommendation on whether or not we keep Talos 1 up or if we bring it down.
It's going to be a decision on up and down for radios based on
bring it down
power.
for now. We're taking the same pictures.
I would not recommend powering down Talos.
He did say pictures.
He did say pictures, yes. So hoping to see the status of Athena on the lunar surface soon. We were initially expecting pictures would take a couple of hours to come down as the flight teams prioritized downloading data and safing the vehicle, but this will help us better understand the configuration of the lander.
Spark 642 acknowledged.
Every time we hear Michaela come on the tunes
Order,
there.
can you zoom in on this view? Actually, give me the spacecraft view.
Spark 644 acknowledged.
Getting all these acknowledgments coming through.
No, take task down.
All right, we're going to see here. Looks like Tim's
Star
got a good
trackers
spot.
down.
Keep powering down things that we're not using anymore. Mission director looks like he's looking up at the screen. Maybe they're looking at a little bit of data that we do not have in front of us. Still standing by for confirmation. Well, we've heard a few steps go through the process, venting the lander's system, hopefully pulling down data inside of mission control, confirming Athena's status on the surface. And then finally, it sounds like we've heard a couple mentions of pictures. We've shown a couple from that descent stage. And we're just going to keep standing by, looking into Nova Control here in Houston, Texas, just down the street from Johnson Space Center, to find out the situation inside of the IM-2 mission with Athena's touchdown. Again, that was about, nominally, the touchdown time is about 14
Spark
and a half
645
minutes ago.
acknowledged.
We're still in contact with the vehicle right now. We know the vehicle has shut down. Its engines are powered down. We are getting acknowledgement transmissions to the vehicle.
All right, team. Keep working the problem. We're shedding power as fast as we can to keep the vehicle in good health. We are generating power. We are communicating through our telemetry radio, and we are working to evaluate exactly what our orientation is on the surface.
Spark 646 acknowledged. Spark 648 acknowledged.
So good confirmations there, right? We know we're getting acknowledgement. We're sending things to the vehicle. We're safing the vehicle. Now it's time to start working the challenge of how is the vehicle, which way is it pointed. Earlier in the show, we talked about the different antennas on the vehicle and trying to work those, but we are charging, which is a very key element to this mission. Looks like the room's filling up with our subject matter experts. Just continue working on this challenge to see where we stand.
Spark 649 acknowledged.
If you see
DS is back in low rate.
You see folks walking on the bottom right hand of your screen underneath the camera. That's because the room's situational awareness is about a 65-inch TV sitting underneath of there. So what they're pointing at could be data, it could be confirmation. A little hard to see from this view, but as you see people exiting the bottom of your screen on the bottom right, there's a television monitor there that's helping them make some decisions. And as we cross over, it's been about 30 minutes since time of ignition for PDI, and we just hit 16 minutes since our nominal landing. If you're just joining us, we know we are sending commands to the vehicle. We have shut off equipment that has not been necessary. We know that we have an engine that has been shut off. We've commanded the vehicle into surface operations. We just heard from Dr. Tim Crane that we are generating power. We're turning things off that are no longer required. We heard one of them being the star tracker. It's one of the tools that we use to figure out Athena's position in space during flight. We're in landed ops. Now we're just standing by to hear what the full situation is. About 16 and a half minutes since nominal landing time, and a little over 31 minutes since Athena commanded her final engine burn.
Spark
PDI.
651 acknowledged.
Like you said, Josh, we are
Order,
communicating.
go ahead and turn on the displays for all the antennas.
We're
Okay,
communicating.
so you're going to see everyone looking up at the screen here. So when they're calling back to order, that's actually
Spark 652
in the
acknowledged.
back left of the bottom right monitor. They're changing screens inside the room, situational awareness, television up front, right in front of the mission director. You just asked to pull up the antenna configurations, trying to figure
Spark
out
653 acknowledged.
which one's pointing back toward Earth, which might be the best one to use. Towards the top of the show and during PDI, when things got a little spicy, we talked about multipath, Leah, and that's something that we expect to happen on the South Pole. It's something we learned from during IM1, quite frankly, with Odie. Being on the surface and radio waves taking multiple paths to get to the same destination. Multipath exists down on the lunar surface just because there are so many different ways. And during IM1, we were sending out signals that were bouncing off the surface, bouncing off of craters, and making their way back to Earth. We took I think it was a Saturday and a Sunday to learn a little bit more about the multipath situation. You mentioned, Leah, Odysseus ended up breaking a leg and then laying down gently on the surface, but that communications does create a problem between multipath and learning about those things. Inside of Intuitive Machines' Lunar Data Network, it's comprised of ground stations all over the globe, the largest
Spark,
one of
that's
them
good
being...
work so far. What else we got?
The largest one's down in Australia. That is the Parkes Observatory. They call her Mary Yang down there, but that really is what helped us pick up those weak radio signals for IM1. That's not the dish we're on right now, but it seems like we do have a great connection from the vehicle. I believe that dish we're using right now is GHY6 in Goonhilly, but I don't have that confirmation right in front of me.
AD, this is Prop. Can you confirm what is getting powered down?
Everything we can right now, Prop.
Copy.
They're powering down these systems aboard the lander because it does take quite a bit of energy to land, but we did hear good confirmation that we are also generating power.
Yeah, all these commands that are going to Spark is code for avionics, right? It's where our power is being allocated on the lander. And we've heard a lot of confirmations of things being turned off. We heard Dr. Crane say we are generating solar power. At last check, we heard Mission Director call out to look at the antenna configuration on the room's situational awareness model screen, and we're still standing by to see where this is going to go.
Yes, power down the chrosonics until we're ready to use it.
It's about 20 minutes now since our intended landing time today. Again, we were expecting that around 11:30 a.m. Central. Teams in the room in Nova Control, that's here at Intuitive Machines in Houston, Texas, just down the street from Johnson Space Center, continuing to evaluate the status of the spacecraft. Continuing to communicate with the spacecraft itself, and just waiting for potentially a photo that would help us confirm its orientation.
I'm just going to wait one and listen in for a couple cues coming into the studio here. Bear with us, folks. Thanks again, folks, for joining us for the IM-2 mission's landing.